Good evening, everyone. We are waiting for everyone to join in, so we'll wait for a couple of more minutes and then we will begin. Thank you for joining in today. All right, I think let's get started now. So good evening, everyone. I welcome you to the webinar on designing right-sized HVAC with load calculations today. I am Yashima Jain and I will be moderating today's session. Next slide, please. Now, before we begin, I would like to thank our program supporters, affiliates, and our CSR support for Solar Decathlon India. Next slide. Now, today's webinar is being conducted by Peter Ramsey. Peter is talking to us from the West Coast of the United States, so it's early morning for him right now. Good morning, Peter. Peter is the founder and CEO of Point Energy Innovations, a new consulting firm focused on working directly with owners and developers in the US and globally on next generation of profitable, low energy, high performance, and decarbonized buildings and industrial facilities. He has received numerous awards, including the Renewable Energy Innovator of the Year, and ASHRAE's prestigious award of Engineering Excellence, an award only given to 4 other times in ASHRAE's 100-year history. He is a graduate of UC Berkeley and a fellow with ASHRAE and the Association of Energy Engineers. For over a decade, he has taught at Stanford University. Today, Peter will discuss the approach and impact of right-sizing and the interrelationships between building systems and their impact on sizing for each other. Over to you, Peter.
Good morning and good evening to you. And thank you so much, Yashima and Prasad. It's really a pleasure to be here. And I think we're going to dive in, but I think there's first a little bit of discussion about the contest.
Yeah, Peter, shall I take that?
Yes, please. Yeah.
Yes. Okay. So Peter's here to talk about right sizing largely on HVAC systems today. And his talk actually connects with a number of the contest requirements. What's shown on the slide over here is the energy performance contest. And you can see that there's a reduction of loads requirement, which is to be clearly defined with clearly defined strategies for building form, envelope lighting, plug loads, appliances, demonstrated with comprehensive energy analysis. Now, Peter is going to talk about HVAC, you would think, based on the title of the talk, but actually he does end up talking a lot about the other stuff that's mentioned in this requirement. So we'll see how that applies. And then his next talk actually will focus on the next bullet down there, which is the integration of low energy comfort systems. And that's not the topic of today's talk. Yashima, when does that happen? Peter's next talk?
That happens in January.
In January,
Next,
okay.
Yeah, first, second week of January. Yeah.
So that's when he'll be covering the low energy comfort systems. And so today's focus is going to be largely on how you reduce loads and therefore have a good way of downsizing your of HVAC system. Next slide, Peter. Yeah, so this actually ties in right with the affordability contest as well, because there we have the construction cost optimization strategies, which include right sizing. And again, Peter's talk ties into that. And he's not going to cover the financing and the life cycle cost analysis, but he might mention it in the passing based on his the case studies that he's going to look at. So the first bullet of affordability is definitely something that Peter will be talking about. Next slide, Peter. And then there's engineering, operations, and contest requirements. So there for engineering systems, again, we're talking about system design and right sizing explained with drawings, narratives, and calculations. And then there's also a requirement for space provision and architectural integration explained with drawings. So I'm not sure that Peter is necessarily going to talk about space provision and architectural integration, but I think you'll start seeing some of this in the talk that he gives. And if you have questions about this, do send the questions in the Q&A box, and then Peter will be able to address them. That's it, right, Peter, in terms of the contests? And then it's over to you.
It wouldn't be a Zoom call without somebody forgetting to unmute themselves. So anyway, yeah, welcome. So I'm going to talk about something that, is very, very important and dear to me as far as this is one of the most fundamental things that I think is part of energy efficient building design. And so let me first discuss what is a load and what is a load calculation. In buildings, we use the term load to quantify a requirement. So in structural engineering, we have a structural load or a weight load, and that's where I think the word load originally comes from as far as using it in buildings. But when we start thinking about electrical systems or cooling systems or ventilation systems, or in the US, we also have to think about heating systems. We think about how much heat do you need or how much electricity do you need? We call that a load, right? So let's say I need a certain amount of cooling for an apartment, and I need to quantify the how much cooling I need. So it could be depending on which unit system you're using. In the US, we use BTUs, British thermal units. But if you're in the UK, they now use kilowatts, or Europe, the metric system. So it can be either kilowatts or BTUs, or there's lots of other units that you could use, but those are the two most common. So we have units that we use for describing loads. So we're going to talk about how do we determine these loads, and the thing about what is right sizing. Right sizing is the idea of providing the building with just the right amount of equipment to meet the load. So it's making sure that, like, if I need 1 kilowatt of cooling, or if I need one, we use BTUs. 12,000 BTUs is 1 ton of cooling in anyway, so 1 ton or 12,000 BTUs. If I need that much cooling, I don't want to put in 2 tons of cooling. Okay, or if I need 1 kilowatt of cooling, I don't want to put in 2 kilowatts of equipment. That's a waste of money, right? And when equipment is too big, it also operates inefficiently. So I think we could make a parallel of, I don't need a jumbo jet if I'm just transporting 5 people, right? It's very inefficient to have a big airplane carrying 5 people. That's a similar thing. Or even a big airplane carrying only half or a quarter full, then it's very wasteful. So that's what we're talking about, right sizing. Okay. So we ask these questions when we're doing buildings, like, how much cooling do I need? How much electrical do I need? How big does the fan need to be? Chillers are when you're in bigger buildings. And I'm going to talk a little bit about bigger buildings today, like office buildings. And then, how much will the building cost? This translates into construction costs. And when you guys get out and become construction and design professionals, you're going to find that one of the biggest things that we talk about in designing and building buildings is how much does it cost? We're always trying to drive the cost down. And oftentimes when we drive the cost down, it drives the quality down. So we don't want to do that. One of the tricks for driving the cost down is the right sizing. If you need 1 unit of cooling, just provide 1 unit of cooling. Don't provide 2 or 3, right? Same thing with electrical, structural, everything. So, all right, let's jump in. So you guys might look at this photograph and say, okay, it's an IT office. When I look at this photograph, I look at, there's loads. There's electrical loads, and there's cooling loads or ventilation loads. And that's what I see when I look at that photo. So I want to start by doing a poll, okay? And you guys have to participate in this. What are the sources of heat in the office building that I just showed you a photograph of that are going to require cooling? So when we put heat into an office, then we have to provide cooling. So it can come from a variety of sources. So Yashima, if you can step in and
Yes.
describe how to participate.
Yeah, sure. So there's a link in the chat box. Everyone, please click on the link and fill in your answers, and then we will share it with everyone.
Now, in this, there's no right answer. There's many answers. So we're looking for you to put in all the things that you think will occur in that space that are going to require more cooling, a load for cooling. Okay.
All right, we're getting some answers in, and we'll wait for a 30 seconds more, and then we will share.
I would imagine, Yashima, that the folks who are on YouTube live are not going to be able to do the poll, correct?
No, they will not be able to do that.
Yeah. Yeah.
All right, Peter, we do have the results. You can just refresh your screen and yep.
Okay, here we go. Great. So I think everybody had the size of the word is in relation to the number of answers. So computers are a big part of cooling loads. Each watt that we put into a computer or a computer monitor turns into heat in the space. And then that requires cooling. So, oops, sorry. Cooling is requirement when you have a lot of computers in a space. Windows, correct. When the sun shines in the window, that requires cooling. People, exactly. People actually emit heat. Each person emits what's equivalent to about a 75 watts or 100 watts of heat, like an old style light bulb. Lighting, that's another one. So lighting equipment, lighting. So that's right. All the electricity that we put into the lights turns into heat. So walls, so solar gain is again the windows. Walls, heat moves through the wall. Even when there's no window, it can go through the wall. So I think you guys got a coffee machines, exactly. Other things that we plug into the wall in office buildings or our homes, and when we use them, those turn into heat. So as you start thinking about it, if you think about everything that we plug into the wall when it's operating, that also puts out heat. So I'm sure you can think of a lot of things like phone chargers and a wide variety of things. So that's right. So this is what I see when I when I look at this photograph, right? And it's in a good way. These aren't like problems. We have equipment to provide cooling that can address all of these things. So we can very rationally and logically, get this right so that people in this space are comfortable. And I'm sure you've been in, either your home or different offices or wherever where it works properly. And I'm sure you've also been in spaces that don't work properly. Maybe a lecture classroom in one of your universities, oftentimes the sizing isn't right for the equipment or there's not enough of it, So as I said, 1 watt of electricity that goes into lights or computers translates into 1 watt of heat into the space that we then want to provide cooling to counteract. Now, if you're in a very cold climate, it's different, right? If you were in northern India or if you were in Germany in the wintertime, or Canada in the wintertime, right? 1 watt of heat in the space is actually a good thing. It allows us to have less cooling or heating equipment. So it all depends on your perspective. Solar load and the heat that comes through windows is actually very significant. And so you'll see buildings that have 100% glass, and that's because it's architecturally popular right now. But when I see that, I don't see a big, beautiful glass building. I see a building that's going to capture a lot of heat, the sun coming through the windows, the conduction through the glass, and then also some windows, there's a little bit of infiltration, meaning air can leak through. And if it's hotter outside than it is inside, so infiltration could also be a load, a cooling load. So when I see big glass buildings, wherever they are, that is in a climate that requires cooling, then it is worrisome. And it's interesting that I live in San Francisco, Silicon Valley area, and the older buildings in this area, office buildings, were designed with smaller windows, not all glass, smaller windows, and then some sort of concrete or type of facade. We don't use brick around here so much, but and so those buildings don't actually in San Francisco need cooling. We're in a very moderate climate here, but the new buildings that are all glass, they do need cooling because the sun is coming through. So anyway, just something to think about. So when it comes time to do a load calculation, there's a whole process for doing that. It's not overly complicated, but it does require a certain amount of focus. And this is a load calculation spreadsheet that you can use. And there's software for doing this. You can make your own spreadsheet, whatever. It's not that hard, but there is a process to do that. And we take every watt of plugs and we calculate that as heat going in the space. We take the windows, we calculate the sun angle and how much heat comes through the window. All those things we can do. And that's that's the right way to do it. The problem that we run into when designers are in a hurry, they use the thumb rules. And I'm sure you guys have heard about thumb rules. And we use thumb rules as human beings in everyday life. Like when we approximate, I think it will take me about 1 hour to drive across town, but it's not exact because traffic, right? So traffic is less predictable than cooling loads, thank goodness. But we can calculate properly instead of guesstimating is another way of saying thumb rule. So there's many thumb rules. The problem is I don't recommend the thumb rules because they oftentimes result in oversizing, because a thumb rule is one that's set up to be, it will work every time. Every time in buildings, thumb rules work every time. And so it means that we're sizing the equipment to work in every building, including the worst buildings from a cooling perspective. So what it is, thumb rules, like 99% of the time, result in equipment that is oversized and too big. And that is what results in wastage of money in construction. And then also equipment is not efficient when it's oversized. So I don't like the thumb rules. I'd rather do proper calculation. And so many times that I've done the proper calculation and I've compared it to the thumb rule, our proper calculation is coming up with a number that's half as big. Now, when we do a calculation, we do typically add a little safety factor, maybe 20%. But thumb rules, so often they come up with 100% safety factor. It's way too much. It's way too much. Okay, so that's the that's the whole thing about right sizing, is do the calculation and then you'll get exactly what you need. Okay, so another way of thinking about this is once we have the right calculation, we also want to think about how do we lower the requirement for cooling equipment, because we want to not only right size it, but we want to also push it down to make our buildings more efficient. If I said to you, you could live in this apartment where you're paying X for the, let's say 100 rupees for the cooling, for the electricity, and you could live in this other apartment where you're paying 500 rupees for the cooling, or whatever the number, which one do you want to live in? You want to live in the one that's got a much lower energy bill. So we want to not only right size it, but we also want to get it to go down. Okay. So here's some of the strategies for lowering the loads. When we're talking about the building envelope, we want to reduce the solar heat gain, and we can do that by two ways. We can get better glass. There's now glass that blocks out the sun, the heat part of the sun. You still get the light, but you could do less glass is another thing. Reduce the conduction through the wall. We can put insulation in walls, right? That's the most simple. There's lots of other things. Looking at thermal breaks, if you're interested or going to be working on getting a good building envelope on the insulation side, look at thermal breaks. That's something really very helpful. Reduce infiltration and ventilation, right? When it's really hot and humid outside, the infiltration through the building envelope or too much outside air coming in can be not a good thing from a cooling perspective. Now, we do need a certain amount of fresh air as humans. And when you're in the middle of the city, you want filters as well, but we need to bring in the fresh air. We need to cool that down. That's another cooling load, is the ventilation requirement. So we want to get it right. We don't want to do too little, but we don't want to do too much. And a lot of buildings now, we're actually using sensors, CO2 sensors, to sense like how much air do we need to bring in when the CO2 starts to rise up. That's what when there's a lot of people in a room, that says, okay, we need more fresh air in there to bring it back down to a normal number. Reduce the internal heat gains is another way to lower the loads. Like and this relates to the lighting and the plug loads, have more energy efficient lighting, or maybe we have a lighting that we don't need during the day because we designed a building that accepts daylight well. It's not glary, and the daylight comes in and we can turn off or dim down the lights. So that's reducing internal heat gains. And then plug loads, more energy efficient computers, more energy efficient screens, or more energy efficient cooking equipment, right? All these things translate into less heat that then is less cooling, okay? All right, so what is the, what's the cost effectiveness of insulation, and how can we think about it? Normally, what we do as engineers, and some of you I imagine are engineers, we think about insulation on a pipe equals lower energy bills. Okay, we just put more insulation and we get lower energy costs, right? But if we think about it, if we have good insulation on the pipe, and let's say we have lower flow shower head, I'm thinking about hot water system right now. If we put those together, like good insulation, and we lower the load, like less water is coming out of the shower head, then not only we're going to lower the energy bills, but we're also going to need a smaller water heater. And that's where the cost-effective energy savings comes from. When you're not only lowering the energy bill, but you're also reducing the size of the equipment. So we like to invest in the passive elements, insulation, better glass, so that our active equipment, our cooling equipment, or our water heating equipment is smaller, the active equipment. So invest in the passive so that the active can be smaller and simpler and lower cost. Okay, so when we invest in the active, we're lowering the loads. So that's a very fundamental thing to remember. It's very, very powerful way of looking at buildings. And, it's many professionals that I, work with that once they get that, it changes the way they think about design. So, let's dive a little bit deeper into some examples of right sizing. I have a story that I worked in Texas on an office building for the state of Texas. And, generally speaking, Texas is this was in Austin, Texas. It's a hot, humid climate, but maybe not as hot as the hottest climate in India. And they do get a little bit of a winter there, it cools down. But anyway, we were designing a building. We were helping an engineering firm in Texas design a building. This is a couple of years ago. And they said, we're going to use the thumb rule. And the thumb rule says that we are going to use 400 square feet per ton for the new building. And that translated in a certain number of tons of cooling. A ton, remember, is a measurement of cooling. And it's like kilowatts. We use tons. A lot of people in India in office buildings still use tons, right? So, and I use tons in the US. We'll be the last ones to change. We're so, slow to go global, so to speak. But anyway, so 400 square feet per ton meant that we needed a very large cooling system. So we went and we measured other buildings. Luckily, Texas A&M University, which was nearby, they had been measuring state office buildings, several of them in Austin for several years. And we said, show us the data, the actual measured cooling requirement. And the buildings were coming in at 750 square feet per ton, 700 square feet per ton. There was one at 800, 850. These are all would result in cooling needs, actual loads that are half of what the thumb rule was telling us, telling that engineer to put in. And we had a long fight about it. I think we sort of compromised, but at the end of the day, we know that the loads are going to be similar to these other buildings. Okay, so that was very, very interesting. When we were able to get the measured data, it showed that we really didn't need all of that. They were using the thumb rule. So that was a early LEED project, LEED Green Building Rating System. And the engineering firm, they were fighting us with all the LEED green things. But once the building got built and had a LEED rating, they were so excited about LEED, and they became a very big advocate of LEED. So we don't, it was very painful process, this designing this building, but the outcome was super because one of the more important engineering firms in Texas became a very big supporter of LEED because they saw that all these things could work. So how about wrong sizing instead of right sizing? I worked on the Asian Development Bank in Manila, Philippines. And we did some energy upgrades after the building was built. And this was actually designed by a US firm, US architectural firm. And, they actually got an award from ASHRAE and all these other things. When we went in there, we looked at the transformers for the building, and they were 45 megawatts. For those of you who are electrical engineers, MBA, right? It's close to megawatts. So 45, they had the transformers, huge transformers. That's like a very large transformer system. But then in the Philippines at the time that we were looking at this building, they had fairly frequent power outages, like every day or in certain times of the year. And so they only had 7 megawatts of generators, and those 7 megawatts of generators would cover the whole load of the building. So this building the transformers were 6 times bigger than what they needed to be. Now with electrical, you need to have, some extra safety factors. So they probably could have gotten away, but let's say, 15 megawatts of transformers instead of 45. So there was 3 times more. Now each one of these transformers, there's many of them. Each one is as big as a car and is made out of steel and is very expensive and heavy. So, and they had to be transported and everything. So very wasteful. Now, and also transformers, they waste a lot of energy when they're oversized. So there you go. Even, big buildings with, international design firms, they're making these mistakes. So now let's talk about good low energy building design. Okay, I've been for over a decade working with Infosys in India, designing buildings and helping them figure out how to get the low energy, cost effective buildings. And they really have very much perfected it for office buildings. So if you're interested in knowing a little bit about, how do you do this in a very practical way in India, I would look up Infosys. And they published a lot of information. And I believe that Infosys is actually guest speaking in one of these lectures or something. So anyway, there's lots of information about what they've done. So let me share a little bit. So this is one of the buildings, office buildings that they built like 5 years ago. And if you see, they have glass. Glass is good. As human beings, we want to be able to look outside, but it's not 100% glass building, right? That when you're in the space, it actually feels very nice. You have daylight, and you can see outside and everything, but it's not all glass. There's so much of these all glass buildings, from let's say, 50 centimeters or so, maybe 75 centimeters down. What is the glass doing for you at your feet? Why is that? It's in my mind, it's irrational. The other thing that they have is, notice how the windows are pulled in, they're pulled back. So the building itself is shading the glass. So when the sun is shining, you get the daylight, but you don't get that direct sun shining in, which brings a lot of additional heat and also creates glare. Right. And the glare is, when you're working on a computer screen, is very, very disturbing and hard on your eyes, and everything can ultimately give you headaches. So this is a very rationally done building design. It also happens to be very affordable because I think they use a precast panel, but whatever, that's all cheaper than the glass. So they do use double pane glass that is also tuned to let in the daylight but block the heat. It's called low emissivity glass, low E glass. And so their facades are great. the amount of heat coming in from that facade, it's not half, it's like 1/4 of what a glass building would be or less. It's so much lower. And then what they also do is they very much perfected low energy lighting. They use the LED lighting that's dimmable and it automatically dims down. And they design it in a way that gives just enough light, not too much light, right? And they also use low energy computers. Now, everybody, well, there's not so many people in the office right now, but they had started the transition over to laptops before COVID, but now everybody has laptops. When they come back to the office, it will be the lowest energy computers that they've ever had, because laptops use a lot less energy than the computers you plug in, desktops. And then they also have very low energy fans. And there's different types of fans out there, but they work hard to find fans. They have some ceiling fans that are low energy, and they also have their ventilation fans that bring fresh air into the building, and they filter it and they dehumidify the ventilation air. So you put all these things together, and this particular building is in Bangalore, but they have buildings in many different parts of India. Emphasis is not, they're not like, remember the thumb rule, even in India, it's around 400 square feet per ton, 500 for office buildings. Emphasis is now building buildings where the design is 800 or 900 square feet per ton, and they're no problem. So they have half as much cooling as sort of the market standard building, and they're operating perfectly. So, wonderful, wonderful way. So that results in smaller chillers. Remember, we also have to have generators to back up the chillers for power outage, right? So that the generators are smaller, and then the electrical equipment is smaller. Remember, I talked about the transformers, the wires, all these things. They actually are quite expensive. So all these things get smaller and cheaper. So that is exciting, right? You do all the right things and it starts to become very affordable. Emphasis is able to build buildings that are, no more expensive than a standard building, in certain areas cheaper than the standard building that is very energy wasteful. So to me, I'm super encouraged. So here's the cooling thumb rule, 400 square feet per ton, but they're doing 800 square feet, and they're normally operating at 1,000 square feet per ton, meaning, higher the number is smaller amount of cooling. And then the electrical infrastructure, excuse me, is, normally you have a thumb rule of 0.8 kVA or kilowatts per 100 square foot. And the actual that they're putting in, installing in the buildings, again, half as big. And that means half as much money. That's good, right? and then also the energy bills are going to be significantly lower. Yeah, emphasis office buildings, they use half the energy of the standard office building in India. Now, and I could show you many examples in the US or in Europe. This all applies. You want it to be climate specific, right? Like the building that I might design in Chicago is going to be a little different than the building that I would design in San Francisco or Bangalore. Each one has its own climate, and the right sizing wants to be based on adapting to the climate. There's not one size fits all. So something to think about. But I did want to tell you, there's these two American companies. One's called JLL, one's called CBRE. They're international companies, and they are very active in India, as well as, US and Europe. And the problem is with like the developer buildings is they say, oh, the requirement is we help tenants find buildings. So they help big companies find office space in buildings that are built by a developer. And they say, oh no, we won't go into a building or recommend a building unless it has this 0.8 kVA or the 400 square foot per ton of refrigeration, TR. And so they're actually, they're a barrier to developers building low energy buildings. It's a problem. And we've been talking to them and working with them on this issue. But, when a company builds their own buildings, when Emphasis builds their own buildings, or any of the other IT companies in India, when they build their own buildings, they can do the right thing right away. They don't have to worry about these requirements from these real estate consulting firms. So anyway, all right, let's do another poll. Hopefully you're following along here. How big is a cooling system for your solar decathlon project? Take the best guess. So if you're doing a office building, you could think about the big system. If you're doing apartment building, you could do by apartment, or whatever. Have the team started to think about this? Yashima, is that something that they might have started to think about? Or
Yes, they have started to think about it, but not in that detail. They will provide this level of detail in the third submission, which comes in February.
February.
So
So
yeah.
maybe should we skip this poll, or
Let's
what do you
ask
think?
Peter and see what we get. Maybe we should ask in terms of square feet per ton.
Okay.
Yes.
Yeah.
All right.
Yeah.
All right. So yeah, go. You can either put it in. Is this a word cloud, or what's the answer look
Yes,
like?
this will also be
Okay.
a word cloud.
So go ahead. You can either put in square feet per ton, just put the units, 400 square feet per ton or whatever, or you could say 500 tons, whichever one you want, or kilowatts, just put in the units in your answer, and let's see what that looks like. Okay, and we can talk about that. Again, there's no right answer, and you might be using a thumb rule to get started, but you're going to be calculating it later. That's fine. I understand. So let's just see, where you guys are.
So there's a link in the chat box. Please use the link to answer your question, and we will share the answers in a bit. All right, we are getting some interesting answers here. I will.
And you can see, I mean, this, for those of you who have already sort of are into this, or have started doing some of these calculations, it would be good to share that. And some of you who have not yet got into that, it's a good thing to think. Now, I'd like to say that the beauty of the Solar Decathlon project is you all have to collaborate with one another. So let's say you're an architect specializing in the design. Now you can understand that architecture has a big impact on cooling, and has a big impact on the cost of the building, how much energy the building's going to use. You can see that it's a collaborative effort here. Electrical, the cooling system designers, the architect, everybody plays an important role in this, coming up with the low energy buildings. And that's why the Solar Decathlon is a team. It's not just an architectural competition.
All right, Peter. So we have the results. You can refresh your screen now.
There we go. Okay, great. Super. Thank you, guys. So 500 square feet per ton. So that is like a good sort of it's a good starting point as you start calculating it. You're probably, and if you're doing the right thing, you'll probably find that you don't need as much. And there's two 500 square foot per ton. 1,000 square foot per ton. That's probably the person who put that in has been starting to calculate out, that we can actually make it work, or they have a building type, or there's not a lot of internal heat gains or something. And then 500 tons, and then this 45 to 50 EPI, as I understand that would be kilowatt hours per square meter, right? So that's like an overall energy consumption for the whole building. Part of that would be cooling, part of that would be lighting. And so that's another way of thinking about energy performance, is that you want to wrap all these things up and see over a whole year how much energy they're going to use. So if you're doing the right thing, like right sizing and reducing loads, those two things together, it will bring your EPI down, or kilowatt hours per square meter per year. So anyway, very good stuff. I really appreciate you guys putting that in. And you can see it's sort of framework for thinking about it. Again, if you didn't put something in, that's fine, but you're now starting to understand the language and the approach. Okay, so a little bit about the plug loads. I have another story for you. I remember once when I was working for a tech company a little while ago, and we had measured the plug loads for computers in many of the buildings for this tech company, and we were coming up with 1 watt per square foot. And that was a measured requirement for electrical. So I was saying, we're going to design the cooling system for 1.5 watts per square foot, because, who knows? They might get a little bit more in there. But this engineer who was also working on a project, he worked for a different company. He got on the phone and he started yelling at me. And he said, and he was really, it's like a really experienced engineer, many years of experience. And he's like, Peter, you're crazy. I can't believe you. We have to do at least 3 watts, but I do every building that I do for the plug load is 5 watts. This building will be horrible, and then he tells the owner, like, if you don't do this, this building will overheat and everybody will go home and be screaming about, and he was just got very emotional about it. And, so often engineers, they go to the architect or to the owner and they say, well, if you don't do it, the building will be a disaster and it's going to overheat. Nobody will want to be in the building. And that's enough to scare owners into oversizing. But luckily we have physics and engineering. We can do a calculation, we can measure, we can do all these things. So we don't have to use the thumb rule. We can actually use engineering, much more powerful. And one thing about plug loads that you should know, it's interesting. I do this in my Stanford class. They say to everybody, tell me, how much electricity does your cell phone use when you're charging it? So that they'll look at their little, cell phone charger, the little brick or whatever they have, and it will have a little small writing in there, and it will say, 20 watts or something like that. Well, it turns out that when because I'm an engineer, I measure these things. When it's actually charging, it doesn't use 20 watts. It will be using 3 or 4 watts or 5 watts. The electrical rating on electrical equipment is always much higher than the usage, the sort of normal usage. And the reason is, when you plug something in, the first time, there's a little bit of a surge. It's very short, just for a second or a fraction of a second. But so that's why the electrical equipment, the transformer for your phone needs to have the capacity for more watts, like 20 watts, when it only really needs when it's charging 5 watts. So it's always, when you're trying to understand plug loads for a new building, like when you guys are doing your design, and you say, okay, well, what's the rating on this dishwater laundry machine or something, or stove or something. Remember that the rating on the nameplate is always significantly higher than what it would use when it's operating. Okay, so and that's why some engineers get all crazy and start yelling and say you have to do 5 watts per square foot, right? So I don't do that. All right. And then there's, when you do a model, when you're doing your calculation for the load, the assumptions matter very much. And so when we do, this is a copy of a thing that I use in my consulting for buildings. When we're actually doing load calculations, I have our team, they fill out a form of what are all the assumptions. What's the assumption for the insulation value of the glass? What's the assumption for the outside air temperature on the hottest day? Let's get very clear about it so that you don't make mistakes. And so again, this is something we do like professionally, and I charge my clients for doing this work because we have to be careful about it. It's not too hard, but you can make mistakes. So just be careful when you're doing these load calculations and make sure you document all your assumptions in a table so that you can share it with the whole team and make sure it makes sense. Okay, so I want to talk a little bit about passive facades and passive design. And I mentioned it earlier a little bit in the emphasis building, how, you know, the windows are not as big, but they still get in very good daylight. So that's, in a sense, that's the passive design. And remember, I said we want to invest in the passive elements of the building, so the active elements are smaller. So passive element includes the glazing and the building envelope. These are passive elements. Now, there's an interesting thing. You guys know about power outages. Wherever you live in India, you experience them here now and again. Passive is good not only because it lowers energy, but passive is also good if you're in a building that doesn't have a generator. You want, and it's a sunny day and during the hot season, you don't want to have to, you know, evacuate the building. And that could happen in an all glass building, office building. It's like a tall tower, all glass, no power. You'd have to leave the building because it would get so unbearably hot. So we want to, if we start thinking about buildings, like how would this building operate if there was no cooling system whatsoever? That's passive. And that's what we call resilient for power outages, which, you know, it's something that more and more we're seeing everywhere in the world. I live in California, you know, very evolved electrical system. And I now, like 10 years ago, no power outages whatsoever. Now I get two or three power outages a year. And it's because we starting to have fires in the part of the state where they have big electrical lines, and those lines get cut. So anyway, the beauty of where we are today as far as passive design, if you think about traditional buildings in India or in any country, there's lots of passive design because traditional architecture was done before there was active cooling systems. But nowadays, we don't have to wait for like 100 years of trial and error. That's what happened in traditional architecture, or 1,000 years or several thousand years, right? But what we have is modeling simulation tools. This is very good. So if you look at this photo on the top left, right, this is a simulation, a computer simulation. There's colors on the windows. That's not an architectural feature. That's the results of the energy model. So we can do an energy model or energy simulation of the building. We can change the overhang in this building. You notice the overhang. We can change the depth of the overhang. We can change how many overhangs there are, and we can try all these different things. And then remember that the orientation of the building, the location as far as latitude in India, you know, northern India is different than southern India as far as the sun angle is different. And we can, and different seasons have different sun angles. We can do all of that now with computer simulation, and we can tweak the building envelope to come up with a building that's more passively survivable and works well with less cooling. So you can see, you know, the lower left is sort of more leveraging traditional language as far as architecture, but there's the bottom right photograph is also a more modern approach to dealing with the solar load on a building. So this is one where the architect really wanted to have all the glass, but they didn't. They were at least smart enough to try not to shade that glass so the building didn't overheat. So there's many tools and strategies now, and that you can leverage in your guys' groups to be able to come up with a system that will be, I like to call it passively survivable, or a passive facade. Now, it's at the end of the day, you're not going to probably come up with a building that will be completely no need for cooling whatsoever. That's not necessarily the goal, but you want it to be one where the amount of cooling goes way down. And then the last thing I did want to say is that we are, as building designers, we now have to start thinking about climate change and how it's going to affect our buildings. So this graph on the right is showing some different cities where we think the maximum temperature is going to be at 2050. So this is 30 years from now. And the, unfortunately, the maximum air temperature, and this is not the average temperature that they talk about in the climate discussions, but maximum temperatures are going to get hotter. So if you, in this graph, Delhi is 3.5 centigrade hotter on the hottest day of the year. New York City, 4. But there's some, I live not too far away from Seattle, 6 degrees centigrade on the hottest day is so we're designing buildings now where we do take into account the hotter expected temperatures. And it doesn't, it doesn't change the size of our systems super significantly. It does change them a little bit bigger, but we still aren't doubling the size of the system and doing oversizing. We're still practicing right sizing techniques and getting, very, very excellent results. So it's just something to think about. Yeah, so I wanted to share with you one of the submissions from the last go around, last year's solar decathlon. And I think it's just a fantastic example of putting this all together. And this is the one from CEPT University. And maybe there's a team this year from CEPT. Is there another team from CEPT? Yes?
Yes.
Great.
Yes,
So,
right, Prasad? Yep. We do have a team from CEPT University.
But the beauty of it is you have access to the information of this submission, and I'm going to share it with you. So it's not a secret or anything. It's just good design. So what this team was doing is they were doing a multifamily housing project, right? And so, apartments and the whole bit. And so they did a lot of modeling of the building. And one of the interesting things that I like about it, if you look at this rendering of the building, notice how there's more of these balconies at the top, the upper floors, and less on the lower floors. They had, it's part of our architectural feature, but they also did this analysis where when the buildings are together, one building shades the lower part of the other building. So the shading at the lower half of the building is not as important as the shading in the upper half. So they were even looking at the interaction between the two buildings, or between the 3 or 4 buildings that they had. So what they did was they came up with different facade solutions or treatments, and you can see how they had they ended up having movable louvers. So this upper left one is when you want ventilation, and the upper right is when you want lighting. And so they had this creative solution where there's this strip of glass above that lets in light. So even if you close the shades on the hottest day, you still are getting some daylight in there, so that your electric lights can be dimmed down or turned off. So they modeled it in a wide variety of conditions, and looked at it, and they tried to, they tried different things. It's very fast in the energy model to try different size of shades or different sizes of windows and everything. So at the end of the day, compared to the base case building, so standard building without the shading and such, the heat gains, that's our load, heat gain from the building envelope. They were looking at the 350 kilowatt hours per square meter, right? And then their design came in, their better design, below 250. Right. So what they were getting in essence is, I don't know what that is, but like 35% reduction in the requirement for cooling at the facade. So that's and just simple. There's nothing high tech about this. It's just simple, straightforward, good design. So I really love that. Then what they did is they used the the star system to get better lighting. They really did look at the lighting. So better, the 5-star system, they got better lighting, And then they also got dimmable lighting. So the better lighting we all now know is LED lighting, right? It's the best kind of lighting, but not all LED lighting is the same, right? Some is more efficient than others. And then also the type of fixture that you have for your lighting does affect how much light gets out and spreads in the room. So it's not just LEDs, it's also what kind of fixture. And then another thing is the color of the walls does affect how much lighting you need or use. So if you have, just to take extreme, black walls, you need a lot more lighting to achieve the same lighting level as if you had white walls. Now, you don't have to do white on everything, but light colors is the key versus dark colors. Okay, so that results in, so they were able to get 38% less lighting. And then they looked at plug loads. So they looked at in an apartment, plug loads are refrigerator, right? They have a stove, and I can't remember what other things they had, probably some plug-in lights and other things like that. But they were able to get 69% reduction. Again, they use the 5-star system. It's a very good system, labeling so you can find the most efficient refrigerator quickly, right? You want to get the ones with 5 stars, not 2 stars, right? So they put those things together, and then they turn it into what's called the EPD, the watts per square meter, and you can see. Oops, sorry. My computer's acting up here. Sorry about that. You can see, that what they were able to get for the lighting power density and the equipment, the plug load. So they have a lower energy facade, less heat gain from the facade. They have less heat gain from the lights and less heat gain from the plug loads. Remember, computers, you guys said it in the beginning, computers, but refrigerators are the same. All that heat, all the electricity that goes in the refrigerator turns into heat in the space. So they were reducing the facade loads, the lighting loads, the plug loads, all those things were coming down, all the things that create heat that require cooling. So you can see they did an analysis here, and one by one, each thing was helping to optimize. So they started with, and this is the right way to think about it, the passive measures, right? The building envelope. So they optimized massing. They thought about the shape of the towers and how they relate to one another. Then they worked on the shading, those operable shades that we were showing. They also looked at insulation in the wall. I talked about that earlier. Insulation actually makes a big difference. And then the window unit, and they looked at the type of glass and everything. So they got very much into the passive measures. And then when they got that under control, they started looking at the 5-star lighting, right? The energy efficient lighting, 5-star equipment, refrigerator mostly. And then when they had all those things together, they did this CAAS, cooling as a service, so that the cooling requirement per apartment became so small that they could actually get one cooling unit that they could share between 5 or 6 apartments. And so they actually came up with this business idea that a company could come in and own the cooling equipment so that apartment owners didn't have to buy their own or anything. And then you just pay a monthly charge to the company that owns the cooling equipment. I thought it was very creative idea, leveraging the fact that they had downsized the cooling requirement so much. So these bar graphs here are looking at the EPI. So the kilowatt hours per square meter per year, okay? So they were able to get a 58% reduction in energy use. If I were talking to a developer, and I do work with many developers who build apartment buildings, they're like, well, the energy use, I don't care so much because my tenants pay the energy bills. I don't care so much. But if I told that developer, I'm going to make your cooling equipment 50% smaller, that developer would be very interested. Right. And that's what they were able to do. The energy use did sort of follow the cooling system sizing. So the cooling, if you look at, was 15, the cooling energy here, 15 units on the base building, the sort of typical building, and then 4.8 units for, this is annual energy use. But the cooling system sizing was probably reduced by, that's like over 60% reduction. It's like 70% reduction. I don't know their final number, but it was somewhere in the 60% reduction in the peak cooling, the maximum cooling needed. So that's, remember what I said, cooling is smaller. And then if you have a building with a generator, most buildings do now, with the generator smaller. And even if you don't have a generator, the electrical equipment is smaller. The transformers, the electrical wires, the service from the utility, all that's smaller. So very compelling, very nicely done. And you know, what they're trying to do when they think about the passive measures, and you guys should think about this, trying to make it not too expensive, try to make it things that you can buy locally that aren't too fancy, they're not too complicated, you know, can be made easily. And I think that their solutions were that, and you know, they're simple and straightforward. So with that, I want to end with some like tips of how I think about these things. Just a little bit of a summary. Assumptions for the plug loads matter. And I say commercial buildings, but apartment buildings, like all kinds of buildings, the assumptions that we have for the plug loads, and also, you know, the approach to plug loads matter. So we can not only reduce the plug loads themselves, but also remember I was saying the power supply, the rating on your computer or your refrigerator on the nameplate is always higher than the actual. The assumptions for hot water use in residential buildings is also something. I didn't talk so much about hot water use, but it's similar. Like, remember I showed that low flow shower head. So we put together insulation on the pipe. It's like insulation on the building facade. And then a low flow shower head. I put together the right elements, and how we do that, you know, that stuff matters. It's simple, but it really does make quite a big difference. And then we can downsize the size of the boiler or the unit that's making the hot water, right? So thermal bridging and correct wall conduction is often wrong. A lot of people don't really think very carefully about the wall and insulating the wall. So if you're getting into the insulation in the wall, if that's part of your responsibility on your team, look into this thermal bridging thing, and you'll get a very good wall. Another thing that matters in the passive facade is thermal mass. So if you think about buildings, traditional architecture, there's a lot of natural ventilation, but also thermal mass, like heavy buildings. And so if you're working in a building, your guys' building, you want to take advantage of the fact most of the buildings in India right now are using concrete. So the concrete actually can absorb heat during the day if it's a hot day. And then I'm sure you've done this at your home, and certain times of the year you can open the windows and it's cooler at night, and then that heat gets released, or the concrete cools down during the night, and then you can close the windows during the day in certain climates, not all climates, and in certain building types. Not like a lot of office buildings, you can't open the windows. But you know, we are doing office buildings where even in office buildings we have operable windows. For right sizing, you need to document and verify the inputs and put them into a model. Okay, so if you're gonna not do thumb rule, which I highly recommend, then what you do is you start documenting the assumptions and you put them into a model of some sort, or a calculation. It could be a spreadsheet at the end of the day, but document and just go through it carefully, and you'll come up with the right answer. And then there is software, and you know, the software can be accurate, but how you use the software almost matters more than which software that you use. So being careful with the software, you know, getting yourself trained up on the software. Now there's so many like YouTube videos about how to use energy modeling software. It's a pretty easy thing to get up to speed, but do take the time for whoever's doing modeling or this different, you know, envelope simulation to you know, get fairly good at it and understand how it works so that you can get results that make sense. So with that, I'll end, and I look forward to having some good questions and discussion with you. Thank you.
Yep. Thank you so much, Peter. I'll jump right into questions. So our first question today is, how should the HVAC designers take into account the impact of climate change for right-sizing their HVAC systems?
Climate change, is that what you said?
Yes, climate
Yeah.
change.
Yeah. Well, I think the main thing that we're talking about is this temperature rise on the hottest day of the year. And so that would be the number one thing if we design systems just to take advantage or to take into account that the peak temperatures are going to be hotter over the coming years. So that won't have a gigantic impact on the size of a cooling system. It will have a less impact if we have better insulation in the wall and better facade. All these passive strategies will work well as temperatures rise. So I think the passive strategies are even more important. And I will say that I think the glass buildings, these all glass office buildings, you see them also in some high-end apartments as well. These buildings will suffer and be difficult to control in the coming years. So, good passive design and taking into account, you can look it up on the internet now. There's predictions for, where we're going to be at 2050 for your different city and things like that. The other thing that we are talking about, and this falls under the category of what we call resilience, and that is resilience in the face of climate change. The other thing that we're looking at is different other climatic issues. And so in my area in California, we're starting to face more droughts, which translates into more forest fires because we have a lot of mountainous areas with forests. And those forest fires emit a lot of smoke for certain. We have like a 1 or 2 month period where these things occur. And that smoke sometimes gets directed towards where people live and towards, cities and everything, even San Francisco. So we're now starting to put in all of our buildings, either place for special filters or even put the special filters in right now, right? So you guys know about, particulates, because in some cities in India really want to take that into account today. But in other areas, you're going to see flooding. In some areas, you're going to see higher winds. So depending on your area, you need to think about, what are some of the more extreme weather conditions that we're going to see, and how do we design a building to address those? So, it's not great news that the climate is changing like this, but, we can design buildings that can account for these things. It's not that hard. It's fairly straightforward. We just need to not get all worried, open our eyes, look forward, and there's lots of information, and say, okay, we're going to design a building that can handle and adapt to these things. Yeah.
Right. Thanks, Peter. Next question. How is the required tonnage per square feet generally calculated for a building?
Yeah. So that's a good question. What we're doing is we start by creating a set of assumptions, like what's the temperature outside, what's the sun angle on the hottest day of the year, and things like this. And then we we start figuring out what are the loads for the building, right? And the process is relatively straightforward. It can take a little bit of time to get all the details together, but okay, we have heat coming through the building facade. So the sun, and then the conduction, where there's temperature difference even through the wall and there's no window, the heat can come through the wall. So there's conduction and solar radiation. And then we have the internal loads, how many lights, are going to be in the space, and are they going to be on, and then what kind of computer equipment, and what is its watts per square foot. And then another cooling load is how much fresh air do we bring in. In some buildings, we actively, like an office building, we have to bring in fresh air. and we have to cool that down. So that's another load. So you look at your building type and you say, what are the loads? That's what we did at the very beginning as a group. What are the loads, computers and lights, and figure out, okay, for each one of these, what's a correct assumption for how is it, how much load is going to come from that. You add all those things together. And then you say, okay, that is my load. Now, what I showed you on that team, the SEP team, is they came up with their loads, and they even did an annual energy model at the beginning, and bit by bit, they would change one thing. They would change the windows, and they would go down a little bit, and then they'd change the walls, and then they would change the insulation, and and one by one, they would improve one element and see the impact. And I really like doing it that way. We know that we need to put all these things together. We know that. But if you can do it one by one, then you can iterate. Let's say, what's the right level of insulation in the wall? Well, let's just stop at when we're going down those bars. We'll stop at the insulation one. We'll try different levels, and we'll find the one that seems to make the most sense and get the biggest impact. And then we'll keep going, So I think that's the right way to think about loads. It's like one step at a time. And you can, if you start with a spreadsheet, then you can always modify the spreadsheet. So start with a simple spreadsheet, and bit by bit, it will get more complicated as you work with your team and they say, oh, did you remember that we've got a refrigerator in the space or a copy machine or whatever, and where does that go into the load calculation?
Peter, I just want to add one thing here for the benefit of this person who's asked the question, as well as others who are listening in. So the self-learning module on rightsizing and rightsizing HVAC systems actually describes the three methods that Peter talked about. One is the use of rule of thumb, which gives the highest size of equipment, and then the kind of spreadsheet method that Peter talked about, as well as the method that the CEPT University team had used, which was simulations, and shows the methods for using these. The spreadsheet method that Peter talked about is also something that is encoded in the handbook by ISHRAE for India with Indian weather conditions. And that's now been put into an Excel tool that's available within the self-learning module. So if you want to use the spreadsheet method, you can just download that Excel tool from the self-learning module on the Moodle site, or you can use your design builder and models to start doing the calculations, since you're doing that in any case. And as Peter said, there's a little bit of learning curve on the design builder models, so be careful. It might be easier and more correct if you use the spreadsheet method, at least more reliable in the beginning. Yep.
Right. Thanks, Prasad. Thanks, Peter. Also, we have a couple of the spreadsheet related questions, Prasad, that we have provided. So one is in the cooling load estimation Excel tool, there is a correction factor for 1.3 for glass and 3 for wall. Can everyone use this value for their project, or will it be different for different projects?
I don't remember exactly. I think the correction factor is looked up in the tables that are in the ISHRAE handbook, and we've provided screenshots of the ISHRAE handbook in the tool. So you can look up the tables and the columns to find, your specific case, what the correction factor would be.
Right.
Yeah.
Yeah. All right. Thanks. Next question, Peter. How do you see the occupant behavior for residential building cooling load reduction or overall building energy performance improvement?
So how does occupant behavior affect that? Is that what you think is the heart of the question?
How do you see the occupant behavior?
Yeah.
Like, do you see occupant behavior as residential building cooling load reduction, or do you see it as an overall building energy performance improvement?
Yeah.
Thing? Yeah.
Well, it's a very good question. In the US, we have a whole conference on occupant behavior and how it affects energy use in buildings, like a whole conference. There's people who spend their whole career studying this particular issue. As an engineer, occupants are somewhat unpredictable. If I could tell everybody, make sure that, your lights are dimmed down, or in the moderate season, you open your window at night so we don't have, and if everybody would do that every time, it would be very easy for me. But, occupants are much more unpredictable. So it's a tricky thing. We have to assume, generally speaking, that people are going to do the right thing. And so when I'm looking at a bigger building, I assume that like for the whole building on average, we're going to get the right behavior. And so, one of those behaviors, if you do have operable windows, or in that SEPT solution, they had the external shading devices. The assumption is that people are generally in the hottest days of the year going to close those things. The louvers, so that it blocks the sun. But there will always be somebody who doesn't do that. And then the question is, for your cooling system, how do you size it? Do you size it that they are going to close the shades, or they're going to forget to close the shades? What do you do, right? And so that gets into a philosophical question, right? So many would answer that on the low energy building. We're not going to give them extra cooling, assuming they're not going to do the right thing on the windows. What we would like to have happen is let that space get a little bit too hot, and it will be a reminder to them, oh, I need to close the shades, right? So there is some philosophy that comes into sizing equipment. That's what I like about engineering. It's not so, and those of you who are architects, maybe I'll give you a little bit more appreciation of engineering. It's not so cut and dry, like there's only one answer. There's definitely a lot of philosophy that can come into it. So there's another thing that we do in buildings. We try to encourage people to do the right thing. So how do we, if we're designing, assuming that they're going to close the shading, how do we give messages to people that that's how the building works? So, what do we do for new occupants of the building? Do we give them a training or a link to a YouTube video, or maybe we put a little plaque next to the window that gives them some reminders or instructions? Some buildings, they actually have little, LED lights that turn on, like today is a good day to open your window. It's a moderate, the pollution's not bad outside or whatever. And so, there's a lot of different ways to get people to do the right thing that you can then start to count on, and then you can factor that into your loads and your right sizing. But I think behavior has a bigger impact on the annual energy use and the comfort in the building. It's not as much on the peak day, but it does have some impact there. But really the biggest impact, behavior on the overall energy use of the building. It's sort of like, leaving your lights on when you're not home. That's something we need to, it's not a peak day thing as much as it's an overall energy use of the building. We got to, get people to understand and to do the right thing, right? And there's different ways of doing that.
So Peter, you talked about operable shades as one of the things that occupants are expected to do, and whether we should count them or not. I think another thing, especially with residential buildings that have operable windows, is we should assume that the windows are closed when the air conditioning is on and that they're not left open. The third thing could be temperature set point. If people are willing to live with higher temperature set points, that will affect the load calculations. And whether that's reliable, and whether, in engineering you do that or not, but that's definitely one of the elements of behavior that could have an impact on the sizing.
Yeah, it's very interesting because, when we're sizing office buildings for emphasis, they're very comfortable with assuming that it's like 26 degrees Celsius inside the building, or sometimes even a little bit higher, 27 and things like that. But when we're doing buildings for tech companies in California, they're like, no, you could never do that. It has to be, it's like 22 or something, so they, there is also I found that different people in different countries have different thermal preferences. Interesting, or tolerances. Yeah.
Yep. All right. One last question for today, Peter. So
Yeah.
our question is, does tonnage depend on number of people? Is there a thumb rule for it? Can you talk a little bit about that?
Yeah, so tonnage, cooling quantity does depend on number of people inside the space. And as there's not a thumb rule as far as, square feet per ton, but there is a number of how many BTUs a person emits. And it's about 250 BTUs, which translates into about 70 or 80 watts. Right. So that depends on like the activity and the size of the person and the age and all these other things. But there's there is a thumb rule on that, which is the 250 BTUs. And then there's a latent part of that, which is humidity that we breathe into the space, which adds to humidity. So it's not just heat. People add heat and humidity. But there is a thumb rule for how much per person, but there's not a thumb rule for the square foot per ton for people. But yeah, each person is a heat source. And so like when we're doing conference rooms, it's always I remember at Emphasis, we designed for like 10 people in a conference room, and they come after the building's built and they have like 25 people in that conference room all, standing, and it's overheated because we designed that room for 10 people, right? So yeah, people really do matter in spaces.
Right. Thank you so much, Peter. Prasad, anything you would like to add before we close?
Nope. Thank you, Peter.
All right. Okay, so thank you so much, Peter, for a very informative session today, and the way you have tied passive design with right sizing. I think it's very important for our students to understand that aspect as well. So thank you very much once again. And I hope our participants have made the best use of the knowledge that you've shared today. And to all our participants, thank you very much for participating, and we will see you next week for another webinar. Thank you.
Thank you.
Thank you.